Hello! In this video, we are going to prove the following theorem. Let a and b be positive real numbers. Then for all positive integers n such that n is greater than or equal to 2, a plus b to the power of n is greater than a to the power of n plus b to the power of n. Now, intuitively, if you apply the binomial theorem to a plus b to the power of n, well then, this is really equal to a to the power of n plus plus b to the power of n. So yeah, it makes sense that this guy should be greater than a to the power of n plus b to the power of n. But in this video, we're going to prove this using induction. So to start out the proof, let's give ourselves two positive real numbers, a and b. And from here, we want to prove for all positive integers n such that n is greater than or equal to 2, this is true. So let's use induction to prove that. So let's start with the base case. Now in the base case, we're trying to prove that this is true in the case where n is equal to 2. So really, we're trying to prove that a plus b squared is greater than a squared plus b squared. So let's start out by writing the left-hand side. Now a plus b squared is just a squared plus 2ab plus b squared. And then, since a and b are positive real numbers, surely 2ab is also a positive real number. And then, if we take this inequality and add a squared plus b squared on both sides, we get that a squared plus 2ab plus b squared is greater than a squared plus b squared. So we have shown that a plus b squared is greater than a squared plus b squared. So we have shown that this is true in the case where n is equal to 2. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n greater than or equal to 2, where this is true. And the whole goal of the induction step at this point is to show that this is also true, where instead of n, we have n plus 1. So really, we want to show that a plus b to the power of n plus 1 is greater than a to the power of n plus 1 plus b to the power of n plus 1. So let me start out by writing the left-hand side. Now, using our rules for exponents, we know that a plus b to the power of n plus 1 is just equal to a plus b to the power of n times a plus b. And now that we see a plus b to the power of n, we could use our induction hypothesis, right? I'm just going to rewrite this inequality right here. Now, since a and b are positive real numbers, surely a plus b is also a positive real number. Well, if we take the positive real number a plus b and multiply it on both sides of this inequality, we get that this must be greater than this. And then if we distribute across these two parentheses, we get that this is equal to a to the n times a plus a to the n times b plus b to the n times a plus b to the n times b. But then a to the n times a is just equal to a to the n plus 1, and b to the n times b is just equal to b to the n plus 1. But then, since a and b are positive real numbers, of course, a to the n times b is a positive real number, and b to the n times a is a positive real number. So their sum is also a positive real number. So if we take this inequality and add a to the n plus 1 plus b to the n plus 1 on both sides, we get this. So this is true. And so, we have shown that a plus b to the power of n plus 1 is greater than a to the power of n plus 1 plus b to the power of n plus 1. In other words, we have shown that this is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step, so this completes the induction step. So because we've completed both the base case and the induction step, we have by mathematical induction that for all positive integers n greater than or equal to 2, this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.